All right, in the last portion of today's lecture, we're going to talk about optimization. So we've defined our model class, we've defined our loss function, and now what we have to do is figure out how to find the setting of theta that minimizes our loss function, our negative log likelihood. So one of the things that it helps to think about when imagining optimization algorithms is what's called the loss landscape. You can think of the loss landscape as kind of a plot of the loss function. So I'm going to use L of theta to denote the loss function. And let's say that theta is two-dimensional, so it just consists of two numbers. You could imagine a plot where the horizontal axes are theta 1 and theta 2, the two dimensions of theta, and the vertical axis represents the function L of theta. And let's say that we are, we have a function that looks like this. So it's a unimodal convex function. Just from glancing at it, you know where the best theta is. It's right there at the bottom of that bowl. But let's say that we don't have the best setting of theta. Let's say that we're at this black circle. Intuitively, what we want to do in order to find the best theta is to modify it so that it moves in the direction of steepest descent. We want to basically find the direction in which the loss function decreases and move our theta in that direction. So a very general sketch of an algorithm would be find the direction v such that L of theta decreases in that direction, and then move theta in that direction. So pick the new theta to be the old theta plus some rate alpha times v, where alpha is some small constant, which is also called the learning rate or step size. Right? Like if you want to use a physical analogy, in the physical world, natural physical objects will fall or roll in the direction of steepest descent, right? If you take a marble and you actually put it in this landscape, it'll go down towards the minimum, and eventually it'll find the minimum and it will settle down there. So that's kind of the intuition behind the algorithms we're going to develop, where we just want to find the direction in which L of theta decreases and then go in that direction. Now, interestingly, the direction of steepest descent is not actually always the best choice, and we'll talk a lot more about other kinds of optimization algorithms in a later lecture. But what all of these methods will have in common is that they will all move in the direction where L of theta decreases, at least locally. All right, and then we just repeat this process. So if we repeat this process enough times, maybe we'll eventually settle down at the minimum. Okay, so let's try to actually instantiate a method like this mathematically. So if we have some function, L of theta, in which direction does L of theta decrease? First, as a quick quiz, what is a direction? How do we represent a direction? Right? Theta is a vector. In this case, it's a vector with two entries. A direction is also a vector, also with two entries. So we need to take L of theta and we need to produce a two-dimensional vector that points in the direction where L of theta will decrease. It's perhaps easiest to think about this in one dimension. So in one dimension, if I'm located over here, the slope of this function will tell me in which direction it decreases. There are only two directions, left and right. So if the slope is negative, that means the function decreases to the right. If the slope is positive, that means the function decreases to the left. So just from looking at the slope, I can tell which way to go to decrease the function. And the same intuition applies in higher dimensions. So in general, you could imagine taking a high-dimensional function and just considering each dimension separately. For each dimension, figure out if the slope is positive or negative. If it's positive, then you move to the left along that dimension, meaning in the negative direction. If it's negative, you move to the right along that dimension, meaning in the positive direction. So for each dimension, go in the direction opposite the slope along that dimension. And what is a slope? Well, a slope is just a derivative. So all we have to do is just set the direction for every dimension to be the negative of the partial derivative of our function L with respect to that dimension of theta. So v1 is the negative of dl d theta 1, v2 is the negative of dl d theta 2. And that is guaranteed to give you a direction where L of theta decreases. Okay, some pop quiz questions. Is this the only direction in which L of theta decreases? Well, the answer is not necessarily, right? In fact, there's an entire half space of vectors that are directions where theta decreases, right? So perhaps these partial derivatives give you the direction of steepest decrease, but if you go a little to the left or a little to the right, you'll still decrease. Now, if you go in the opposite direction, then you'll increase. In fact, so long as you have a positive dot product with V, you will go in a direction where L of theta decreases. So it's not a unique solution. It's not a unique decrease direction. It is the steepest one. That doesn't actually necessarily mean it's best. Right. But that's the choice we're going to go with. And a very useful concept for doing this is something called the gradient. The gradient, which is written here using the gradient symbol, is just a vector where every dimension of that vector is the partial derivative of our function with respect to the corresponding dimension of theta. So V here is just the negative of the gradient. Right? So the gradient is formed by taking partial derivatives and stacking them up in a vector. And we'll go into a lot more detail about gradient descent and related methods in a later lecture. But for now, here's the sketch of the algorithm. Step 1, compute the gradient. Step 2, set theta to be theta minus alpha times the gradient. So the gradient is just negative V here. This is exactly the same as the algorithm above, but just instantiated to use the gradient. The algorithm above is more general. It could use any direction that decreases, and the gradient gives us one such direction. So this is the gradient descent algorithm. All right, so at this point, we've actually selected our optimizer. Our optimizer is gradient descent. So we're ready to run our algorithm on a big GPU. What is this algorithm called? What did we just design? Well, we just designed a method called logistic regression. Logistic regression is not deep learning, but a lot of the concepts in deep learning that we'll discuss actually take their inspiration from logistic regression. So to summarize logistic regression, you have some function f theta of x. And that function outputs an n-dimensional vector for a problem where the label y can take on n different values. So for every possible label y, there's a corresponding theta y. And each dimension of this vector is given by an inner product between x and the corresponding theta y. You can write this as a, in matrix notation by saying that f theta of x is equal to x transpose times a matrix theta, where x is a column vector, so x transpose is a row vector, and it's multiplied by a matrix where every column is the theta corresponding to a different label. So the first column is the theta vector for the first label, the second column is the theta vector for the second label, and so on. So now if you just imagine what this matrix multiplication looks like, when you do matrix multiplication, you take every column of the matrix on the right and then dot it with every row of the matrix on the left. But there's only one row, so that means that you end up with a column vector where every entry in the column vector is just the dot product between x and each of the columns of our matrix. So we can write f as just, in matrix notation in a very simple way, as just x transpose theta. And then the probability that y takes on a particular label I is just given by the softmax function applied to the output of f theta of x. So remember, f theta of x outputs a vector with m entries, and the softmax function takes in that vector, and the ith output of the softmax function is the exponential of the ith entry in that vector divided by the sum of the exponentials of all the entries. And that ensures that our probabilities are all positive and that they all sum to 1. So that gives us this logistic regression algorithm. The parameters theta define these lines that separate the classes, and the probability of a given class increases or decreases away from that line. And the way that we find the best theta, the way that we learn theta, is by using gradient descent. Now, we need a bit of calculus to actually calculate these derivatives, But in principle, we have everything we need, right? Because we have the functions, so we can just use the rules of differentiation from our calculus course to calculate these derivatives. In a later lecture, we'll actually discuss automatic differentiation and how we can automate the process of calculating these derivatives so that we don't have to do it by hand. Our loss is the negative log likelihood, and that's basically all that we need to know in order to implement logistic regression. All right, as a little exercise, let me go through a particular special case of logistic regression when you have a binary label, when you have only two classes like cat and dog. In that case, there's a nice little simplification that happens, and while that simplification is not that important, I think some of the algebra is, it's a little bit informative and useful in some other places, so I just want to go through that and give you that example. So what do we have only two classes? We have y1 and y2. The logistic regression probabilities can be given by this equation. So here I've just substituted in f into the softmax. So p of y1 is e to the theta y1 dotted with x divided by the normalizer. And the trouble here is that having both theta y1 and theta y2 is a little redundant. Why? Well, because if you have exactly two classes, then p of y1 given x plus p of y2 given x is equal to 1. So if you know p of y1 given x, you can recover p of y2 given x. So what we're doing here is we're over-parameterizing this function, meaning that we're using more parameters than we actually need. Here's a little bit of algebra that can illustrate why we don't need so many parameters. Let's take this equation, and let's multiply both the top and bottom by e to the negative theta y1 dotted with x, right? If you multiply both the numerator and the denominator by the same thing, that doesn't change the equation. And now notice that when you have the product of two exponentials, you can just write that as the exponential of the sum of their exponents. So you can equivalently write this as e to the theta y1 transpose x minus theta y1 transpose x. And in the denominator, you have e to the theta y1 transpose x minus theta y1 transpose x plus e to the theta y2 transpose x minus the theta y1 transpose x. So, of course, the y1 minus y1 bits will cancel out and it'll turn to 0, and the exponential of 0 is 1, right? And the same thing happens in the denominator. So we're going to actually simplify this function considerably. Let theta star, or sorry, let the theta plus be equal to theta y1 minus theta y2. In this case, the above equation simplifies to just 1 over 1 plus e to the negative theta plus dotted with x, which is a simpler equation. But notice here now that we have half the number of parameters. We don't actually need a separate theta y1 and theta y2. All we need is theta plus. In general, the softmax is always overparameterized. You can always take out one of the theta vectors. But people usually don't bother doing this when there's a large number of classes. If you have like 1,000 classes, taking out one of the vectors doesn't really save you anything. But if you have two classes, taking out one of them reduces the number of parameters by a factor of 2. So this is an important special case. And this function is sometimes called the logistic equation. This is actually where logistic regression gets its name. The multi-class version of logistic regression using the softmax is actually a later innovation. The original logistic regression is binary, and it's called logistic regression because it uses the logistic equation to arrive at the probability of one of the classes. And this is what the logistic equation looks like. Much like the picture I showed you before, it saturates to 0 on the left and to 1 on the right. It's also sometimes referred to as a sigmoid. All right, the last concept I want to very briefly cover is a particular bit of terminology. You will sometimes hear people say when they're doing supervised learning that what they are doing is empirical risk minimization. Let me just explain to you what those words mean. Let's think back to the 0-1 loss. Right, the 0-1 loss is 0 if you get it right and 1 if you get it wrong. I have a small typo on this slide. This is actually the -1,0 loss. The 0-1 loss wouldn't have the negative sign, and it would be a delta function of x is not equal to y. But don't worry about that. It's just a very mathematically complex way of stating a very simple thing, which is your loss is 1 if you get it wrong, 0 if you get it right. Okay, that's 0, 1 loss. 1 if wrong, 0 if right. You can think of risk as the probability that you will get it wrong, right? Think back to our generative process. Someone takes a picture, it's a randomly sampled picture from the distribution of pictures, it has a label sampled from the true distribution of labels given that picture. What's the probability that you'll get it right or wrong? Well, the probability that you'll get it wrong is just the expected value of the 0, 1 loss. So how likely is it that f theta of x is wrong? It's just the expected value of 0, 1 loss, right? So you can call this the risk that you will get the wrong answer. Now, this is all for 0, 1 loss, but you can generalize this notion to other losses. You can say that, well, if for the 0, 1 loss, the risk is the expected value of the 0, 1 loss, you could say that for some other loss, it's just the expected value of that loss. It no longer has this nice interpretation of being the probability that you'll get it wrong, but it's still a number that you can quantify. So if we're using the negative log likelihood, we could say the risk is the expected value under the true distribution over x and the true distribution over y of the loss that we will get for that x and y and our learned theta. So the risk is what you actually want to minimize. The trouble is that you can't actually calculate the true risk because you can't just sample willy-nilly from p of x. You can't just get infinite samples. Instead, you're given a data set. All you have is d. So what you can calculate is what's called the empirical risk. The empirical risk is just a sample-based estimate of the true risk, which you get by averaging your loss over all of your samples. So the empirical risk is what we're actually minimizing when we're doing supervised learning, but the empirical risk is hopefully close to the true risk. Okay, we could ask at this point, is the empirical risk actually a good approximation to the true risk? When is it good, and why is it good, and when might it not be good? Let's talk about that a little bit. So supervised learning is usually empirical risk minimization. Is this the same as true risk minimization? Well, there are two settings that might give you trouble, and in the first one of these, that's actually the situation where the true risk and the empirical risk are not the same. And this is the setting of overfitting. Overfitting happens when the empirical risk is low, but the true risk is high. So that means that your average loss on your training set is low, but the true expected value of your loss is not low. That might seem a little strange because, of course, your empirical risk is an unbiased sample-based estimate of the true risk. But remember, you're using those data points to actually learn theta. So theta gets coupled to your training points, and your estimator is no longer unbiased. If that's a little confusing to you, there's a much more intuitive explanation of overfitting. Let's say that I'm trying to fit this line, and the dots correspond to my training data. So the dots basically lie on the line, but there's a little bit of noise that corrupts them. If I fit a very high degree polynomial to those dots, I'm going to get kind of a crazy function like this. This crazy function has very low empirical risk because it passes right through the points, but its true risk is going to be quite high. So it can happen if the data set is too small, or it can happen if the model is too powerful, meaning your model has too many parameters, too much capacity. In this case, it's happening because I'm fitting a high degree polynomial with many more variables that are necessary to fit those data points. So that's when the empirical risk differs from the true risk. Another situation that can get you in trouble is where the empirical risk does match the true risk, but you're getting what's called underfitting. Underfitting is when the empirical risk is high and the true risk is high. So here, for example, the true function maybe is a kind of a curve, but we chose to fit a line to it, and the line is just not a good fit to that curve. So this can happen if the model is too weak, it has too few parameters, or too little capacity. In deep learning, this can also happen if your model is just fine, but your optimizer is not configured well. Maybe you used a really bad learning rate, or you chose a really bad optimization algorithm. That can also result in underfitting. Overfitting and underfitting are very, very important concepts. If this is not completely clear to you right now, don't worry about it too much because we will talk about it more in a later lecture, but this material is very important and we will come back to it again. All right, so just to summarize what we covered, in this lecture, we went through how we can derive our first supervised learning algorithm, which is logistic regression. We talked about how to define an algorithm. We need to basically make 3 choices, and then we need to do a 4th thing, but the computer does that for you. So the choices are define your model class, to define your loss function, and to pick your optimizer. And then the fourth thing, which the computer does for you, is like actually run on a big GPU. The model class we chose is the logistic model, where we have a function f, which is linear in our inputs and in our parameters, and then we apply the softmax to it to get probabilities. We chose the negative log likelihood as our loss function, and then we used gradient descent to optimize it. In the future, we'll talk about other optimizers, other model classes, and we'll even talk about other loss functions. But for now, hopefully this gives you some sense for how we can build up these machine learning algorithms, and we'll talk about them in much more depth later.